Okay. All right. Hello, everyone. Welcome to the ARID kickoff. If you can grab your seats, please. Yep. Thank you all. Ben, need to come up then. Hello, everyone. Welcome to the ARID kickoff. We're super excited. I'm not going to speak too much. I'll just introduce myself. I'm Andrew Feldman. You maybe saw an email from me, but I'm speaking on behalf of a lot of scientists that are in the room helping with the proposal, as well as many supporting us as well. We thank you all. We're going to have a nice session here, but this is a first of many sessions. So if you can't make everything in this, that's okay. We'll have some listening sessions, QA sessions. We're going to talk about, we'll have an introduction from Ben Poulter about the NASA Terrestrial Ecology Program, explain that. We'll have a talk from Sasha Reed, who's our PI, our fearless PI and leader. And then a nice talk, a history of remote sensing and ground data from Steve Running. And then even a talk from Jim Tucker, who's actually in the hospital. He's giving a talk from his hospital bed because he believes so strongly in drylands that he will give a talk from when he's not in good health. So, so thank you all. So Ben, please come up and yeah.
Okay. All right, thank you. Thanks, Andrew. So thank you everyone for joining in person, and for the folks online. I think the last I saw there were roughly 100 people online, which is fantastic. So on behalf of the ARID team, we are super excited and enthusiastic to kick off the scoping study. And the presentation that I'll do for the next sort of 10-15 minutes provides some context for how we think about the scoping study in terms of the NASA Earth Science Directorate's Terrestrial Ecology Program. And so I'm a scientist at the NASA Goddard Space Flight Center. I'm in the Earth Science Division in the Biospheric Lab, code 618, for those of you familiar with our org chart. And I've been at NASA for about 7.5 years now. Oh, presenter. Oh, I see. It's like up here, right? All right, hold on. We're just changing the. You want me to try this one? That. No, now it flips this way. All right. Sorry. Okay. Let me try. Well. All right. We're just working on the slides.
You had it for a minute there.
Can you just go? Just put it in present. Can you present right now?
All right, I'll pass it to you. Oh, I see. Duplicate.
Then you
nice. Okay. All right. So we should be good online and in person. All right. So yeah. So all right, so yeah, so here we go. So so the NASA Earth Science Directorate has several there's several directorates that cover different aspects of remote sensing, either for the Earth sciences or for planetary sciences, heliophysics and astrophysics. And so within the Earth sciences, hold on, I am going to close these. I know there's a trick for getting rid of this. Hide controls. There we go. Thank you. All right. So a lot of the mission statement for the Earth Sciences Directorate is related to how we can understand Earth's interconnected systems, all the way from the leaf to the globe. And as we are all aware, the Earth is currently facing unprecedented challenges in terms of various components of the support system that Earth provides to sustain life. And so I just wanted to put this concept of the planetary boundaries here, where at the Stockholm Institute, there's reviews of different indices of planetary health related to climate change, the use of fertilizer, biodiversity. And you can see over time, these planetary boundaries have tended to proceed in the exceedance of how these planetary boundaries can be maintained within a safe operating space. And The work that we do in the NASA Earth Science Directorate is related to being able to monitor changes in Earth system health and to be able to use that information to help improve how we manage the Earth system. Okay, so this is just an example of NASA's current program of record, or the operating satellites that we have in low Earth orbit. And I'm sure some of you are familiar with the different acronyms that are flying past. Missions like Landsat, that's operated by the USGS, but developed at NASA. Missions like OCO2, which is measuring column concentrations of CO2, and so on. And so we have an active area of monitoring the Earth system in low Earth orbit, but also in different orbital configurations. So where does NASA sort of get the guidance to produce the different spacecraft and suborbital missions? It comes from the National Academy's decadal survey. So the most recent decadal survey was published in 2018. It's referred to as the 2017 decadal survey, which is when it was wrapped up. And the decadal survey surveys, it has 5 different science subcommittees that evaluate and communicate, go out to the community to solicit feedback and guidance on how to inform the next decade of NASA's Earth system observations. And the 2017 decadal survey broke this information down into 35 key science and application questions that are contained within these different elements of Earth system observations, including coupling the water and energy cycles, ecosystem change, extending and improving weather and air quality forecasts, and so on. And so the most relevant focal area for us today comes under the ecosystem change element, where the key driving questions relate to what are the structure, function, and biodiversity of Earth's ecosystems and how are they changing? What are the fluxes of carbon, water, nutrients, and energy between ecosystems and the atmosphere? And what are the fluxes of carbon, water, nutrients, and energy within ecosystems, and why are they changing? The decadal survey makes recommendations for these new observations within several different tiers of observation of observing systems. And so this graphic here is showing what we refer to as the designated observables. And so these are directed missions that are currently in development and would form part of a larger observing system or observatory that's referred to as the Earth System Observatory. And so we have this 5 missions on this figure. The clouds, convection and precipitation, and aerosols has been combined to a single mission, the atmospheric observing system. And so there's 4 key missions. I work most closely with the surface biology and geology team, which is led by Dave Schimmel at JPL, where SBG will develop 2 spacecraft, one a hyperspectral or imaging spectrometer measuring reflectances or radiances from the visible to shortwave infrared. And then there'll be a second spacecraft measuring emissivities with a thermal imager. Other missions listed here are mass change, which will be similar to the GRACE mission or the GRACE follow-on mission, and surface deformation and change, which will be a radar-based mission. Then there's another tier of targeted observables, and these will be competed missions where you can see, I think, roughly 7 observables of the Earth system. That includes snow cover, 3D ecosystem structure, greenhouse gases, reactive gases in the atmosphere. And the competition for the down select of these targeted observables just closed in August. And so in about a year from now, we should know which of these observables goes to step 1. So it's another component of the decadal survey, and one that has gained much more traction in recent years, this being the year of open science for the federal government, is how we distribute and serve data to the public and the stakeholders. And so 2 or 3 years ago, the Veda dashboard was developed by the computer scientists, different NASA centers, where Veda is a way to provide access to data sets that are available on the cloud, and then to support the development of Jupyter notebooks to access and analyze and visualize these data sets. And I think just this week or last week, one of the data archives that NASA supports, one of the DACs, just moved its entire archive onto the cloud. And so this is the vision for all of the DACs, is to in the next several years to have all of NASA's data sets available on the cloud, so you don't have to download to do your analysis. And then you can use dashboards like Veda or other cloud-based architectures like Cyverse to access these data sets in a more efficient way. So that sort of brings us to the current and planned program of record for NASA. And so this image is showing the different missions from the age of the mission being closer to the atmosphere of the Earth, to the planned missions coming out to the edge. And so you can probably see some of your favorite missions that are listed here. Again, we have Landsat, OCO. We have the missions on the space station on the inner ring here. So this includes EcoStress and JEDI, OCO3, EMIT, which is a hyperspectral mission on the Pathfinder with acquisitions targeted for mineral mapping. And then we have the planned program of record coming out, where SWOT and Tempo are now launched, and Tropics. PACE will be launching in the spring of 2024. So PACE is an ocean hyperspectral ocean mission with hopefully some applications for land retrievals as well. In addition to NASA, it's not the only space agency. We have the European Space Agency, the Japanese Space Agency, and so I wanted to highlight some of the missions that are supported by ESA. There's a lot of partnerships with both the existing missions and the planned missions between the agencies. And so, for example, with the surface biology and geology mission, there's harmonization activities taking place pre-launch so that we can more easily combine and co-develop algorithms with ESA's hyperspectral mission, CHIME, and SPG. And then beyond the public space agencies, there's been this boom in commercial space with companies developing instruments for hyperspectral, thermal, potentially LiDAR, and radar applications. And so NASA works closely with new space or commercial space in evaluating and integrating these new data sets. So then, sort of moving a level below the orbital missions, we have NASA's suborbital program. And there's a fleet of aircraft that are used to host any number of payloads or instruments that can collect information on reflectances, vegetation structure, atmospheric trace gases. And these missions are done in part to test out new technologies, but also to support current missions through calibration and validation activities, or to provide more targeted measurements in areas where the coverage needs to have more dense temporal frequency or higher spatial resolution. And so this is sort of a rough idea of where these campaigns, these suborbital campaigns, have taken place, but there are some sort of missing examples. And this month, the NASA Earth Science Directorate is flying in the Cape Floristic region of South Africa as part of the NASA's first biodiversity-specific field campaign called Bioscape. So that's a bit about NASA's program of record, and now just moving into some examples of the field campaigns that NASA has carried out. ARID is responsive to what we call the A.4 ROSES element of NASA's funding program, and NASA is currently searching for a successor to the Arctic Boreal and vulnerability experiment, which is a 10-year campaign that's been taking place primarily in Alaska and some parts of British Columbia and the Yukon territories. And these campaigns typically take place for about 10 years. And so above is the fourth field campaign to have taken place. And I just took the text from the request for proposals here, where it sort of defines the boundaries on what the scoping study should look for. And so the scoping study should be looking for science that answers big questions targeted at the regional or biome scale. The scoping study should look to enable more effective interpretation and analysis of the space-based measurements. And so again, this sort of highlights the importance of the suborbital or the aircraft component. The campaigns should foster collaborative interactions and build new relationships within the scientific community. And so this morning with the stakeholders that we engaged with sort of highlights how we're looking for those new opportunities. It should provide valuable opportunities for training and educating the next generation of scientists. And so Sasha will sort of point out the timeline that we're working toward, where really we need early career scientists involved now, so that when the campaign does start, there'll be folks available to collect the data and be involved. And then the campaign should leave a legacy data set of great value for future research. And so the image on the right here is one of the first field campaign, or I think the first field campaign that NASA established. It's the Fife campaign, which took place in the boreal regions. And this took place in the early 1990s, where it was really the first time that scientists were able to explore the connections between the retrievals of reflectances being made from space with the actual vegetation properties and vegetation processes. And so this established this sort of multi-scale image that you can see on the right here, where you have plot measurements, helicopter, aircraft, and then up to the low Earth orbit missions. So Fife sort of established a framework for how these field campaigns could take place, and that led to NASA's first boreal field campaign that took place between 1992 and 1999. Again, it sort of leverages this idea of multi-scale measurements and bring this together to understand regions or biomes. And one of the key sort of findings of Boreas was that scientists confirmed that photosynthesis can be measured remotely and scaled to space, which is something that we take for granted today, and we'll hear more about in Steve's presentation, I'm sure, and from Jim Tucker. Boreas was followed by the large-scale biosphere atmosphere experiment in Amazonia. So this took place from 1998 to 2011. And on the right here, you can get a sense of where the field studies and the flights were taking place across Amazonia. And there's a lot of incredible science that came from LBA. And so I just highlighted here that one of the key findings was that tropical forests are much more dynamic seasonally than what was thought of previously. And this led to sort of key developments in model development, but also some insights into how we think tropical forests will respond to climate change. And then currently, the Arctic Boreal vulnerability experiment is taking place. And I think from my perspective, one of the key sort of findings here is being able to have that critical data to develop regional greenhouse gas budgets for the Arctic, and to be able to understand the vulnerability of these greenhouse gas budgets to climate change. But there's also been a tremendous amount of research on permafrost, vegetation structure, disturbance, and linkages and applications to knowledge related to indigenous communities in the region. And so lastly, that brings us to ARID. NASA currently hasn't ever carried out a field campaign in dryland systems before. And so there's sort of a tremendous opportunity to fill that gap. There are some sort of legacies and shorter term field campaigns that have been carried out in dryland systems. And so I'm just highlighting the Sahel Apex campaign that Niall Hanan was involved with, and the Safari 2000 field campaign that Bob Swap was involved with. And these were sort of superimposed on this idea of the International Geosphere Biosphere Program terrestrial transect concept, which is something that is still very actively sort of used as guidance for field research in dryland systems across the world, including Australia. So that is my overview on the NASA sort of approach in terrestrial ecology to using remote sensing, with some reflection on these field missions. And so I'll turn it over to Sasha. Thanks. To set you up. Where is your, okay. You're on the desktop, right? There. Okay. All right, and then we did this trick here. Oh. Okay. Oh, and then this right here. Scan the tracks. There you go.
All right. Does it look right online? Okay. Good try. Any suggestions?
Yeah, kind of new share.
Where's new share? Yeah. Good work.
Thank you. Let me do one thing.
It looks right. All right, we're getting it. Excellent. Well, dryland people of Earth, I'm so excited about this opportunity for big science in these ecosystems that we love and recognize as so important. And so let's see if we can change the slide here. Ben did a spectacular job of introducing the NASA terrestrial ecology program and the opportunities for large field experiments that couple on the ground measurements with drones and airplanes and satellites. And those are the kinds of approaches that we're going to need for the challenges that we face in terrestrial ecosystems today. And so it's hard not to doom scroll climate change when we look online. We see lots of changes that we're worried about, like these high temperatures in already hot places, huge storm events, flooding and extreme events, fire, drought, changes to water cycle and the availability of water, our ability to produce energy. These are big, scary changes. And so we want to better understand these changes, not only so that we can address them head on, but so that we can get creative about solutions and ways to manage in the face of this change. And part of what makes them so daunting is how complicated they are. So we have ecosystems that interact with at the organismal level, across landscapes, within regions, and at the planetary scale, as well as everything in between. There's biotic and abiotic controls that are working together antagonistically, synergistically, in ways that are really hard to quantify and really hard to understand. But that understanding is what we need in order to make the kinds of decisions that we hope to sustain these ecosystems and the services that they provide into the future. And these challenges may be particularly challenging in drylands. Drylands, we know by definition, are low in the resource of water, but they also often have low soil fertility. These are just data of mine from a temperate forest in Massachusetts, tropical rainforest in Costa Rica, and a semi-arid grassland in Utah. And you can see how low the total soil nitrogen is in those soils. So we're trying to manage for systems that are really hard to put back together once we take them apart, because they have such low background resource. We also have extremely fast changes to things like temperature. So this is the temperature scale for Australia from Australia's Bureau of Meteorology. They had to add a new color because things are getting so hot in Australia. The old temperature range didn't cover the hotness anymore. And that's in a dryland, a place that's already hot. So we have these hot places getting hotter, dry places getting drier. What is it going to mean for the organisms that live there, including us? This visual shows Earth. It's hard to see the outline of the continents, but the yellow is dryland ecosystems. We define them in different ways, and that's worth thinking about. But no matter what, we think they are enormous. We think they are vast sets of ecosystems covering more than 40% of Earth's land surface and providing lots of ecosystem services. So if you ask most people to close their eyes and picture a dryland, they will picture a vegetation-free sand dune that they don't think is probably very important in the carbon cycle, in decision making, in land management. But all of us know that that's not the case. These are critical ecosystems making up more than 40% of the land surface, supporting more than a third of the global population, including many people who live very closely tied to the land, who do not have a lot of resources to find another place to live, to find another livelihood. 60% of our food production, which is not something that I knew. And so that's an enormous amount of service there. 40% of the net primary production, dominating the trend in the interannual variability in the land carbon sink and in atmospheric CO2 concentrations, 38% of soil organic carbon, 80% of soil inorganic carbon, much more poorly understood cycling. So these are really important ecosystems at the Earth scale for understanding services that sustain our species, for the regulation of climate, and for a wide host of things. These are also systems that are changing really fast. Here we have a heat map of the temperature change between 1895 and 2018. The hotter colors mean faster temperature change over that more than 100-year timeline. And we see these southwestern ecosystems as being hotspots of change. This is the order the data were grouped by county in the United States. So this is the number one fastest warming county. Here's number two, Grand County, Utah. That's where I live, in Moab, Utah. So these are really fast changing systems that are already so hot, it's hard to imagine them getting hotter, that are getting hotter. So how is that going to affect ecosystems? How can we manage in the face of that change? We also know that dry places are getting drier. We're still thought to be in the worst drought in over 1,200 years. We've had some good winters in some places. We're hopeful about the future, but overall, we're seeing increased frequency and intensity of drought in these places. And we know that that can do things like interact with exotic invasive plant species to result in massive fire events, huge increases in the timing of fire regimes that used to be very long in between fires that are now becoming very short and are really really transforming ecosystems quickly. We also see this in things like soil destabilization. This is a huge dust storm moving into Phoenix, Arizona. Dust is the second highest cause of vehicular death in Arizona. It carries disease like valley fever. There are direct consequences of increased dust to our health, and then also lots of indirect consequences. That soil fertility that I showed you before. Dust is a loss of fertility, typically from one place blowing to another place, changing albedo and snow dynamics and melting. This highlights the connectivity between these ecosystems. Unlike Vegas, what happens in drylands doesn't stay in drylands. And so we really need to be concerned not only for those of us who live in these ecosystems, but for those of us who live on planet Earth, which I think is all of us. So it's also exciting to think about the opportunities for land management and science-informed land management in drylands. These different colors represent different land areas by Bureau of Land Management in the yellow, Forest Service, Fish and Wildlife Service. And what you can see here is that public lands dominate the Western US, as do drylands. So we have tasked a lot of land managers with managing these dry ecosystems, and now we have climate change on top of that. We have an opportunity to help support that management through science that can not only help us better understand the challenges we face, but better understand the opportunities that there are for improved things like restoration. There are also huge amounts of tribal lands and public or in private lands. All of these resource managers are working to make decisions, and the kind of science that a terrestrial ecology field campaign could produce could be transformative in informing those land management options that could make a big difference. It's also really exciting to think about the ability of scale. So for example, the Bureau of Land Management is almost 10% of the United States land area. If we could find information and help the Bureau of Land Management change policy based on that information, for something like we're working right now with BLM on carbon management on public lands, we could overnight massively become a leader in carbon land management globally because public lands are so vast and because in theory we have the ability to make these decisions at a national scale about those public lands. And so, as Ben said, the NASA Terrestrial Ecology Field Campaign is meant to address big, complicated systems and problems. We see here that it includes on-the-ground data collection. This is the kind of data that I do right there, hunched over, plants and soils. We can do things like eddy covariance and other ways to better understand exchange between the biosphere and the atmosphere. Numerical models help us scale across space and time in ways that it's really challenging to do with empirical data. Drones, airplanes, and of course satellites, that these big opportunities for cross-scale science, multidisciplinary science are in some ways our best hope at addressing these really complicated issues of climate change, especially in places like drylands where we know things are changing fast. It's also exciting times, as Ben showed so nicely, in what remote sensing tools we have at our fingertips. So this paper by Bill Smith and others looking at some of the different ways that we can sense ecosystems from satellites, from drones, and the different traits of the system that can be assessed based on that. We're really exploding in the way that we can remotely sense an understanding of how ecosystems work and how they're responding to change. And that's especially interesting for drylands because they've posed some challenges to remote sensing data in the past where so much bare soil is being shown, or biological soil crusts, things that we're not accounting for in lots of these other ways we're measuring systems. So it's really cool, the new tools that are coming on deck, the increased spatial and temporal resolution that we're being able to see, and they may be particularly powerful in dryland settings. So a new NASA Terrestrial Ecology Field Campaign is an enormous opportunity for science in general, and NASA wants the scientific community to be able to take advantage of it by spending some time scoping across the community. So what they do is they ask for scoping study proposals. This happened in winter 2022, and then they pick 2 of those proposals to move forward. Those 2 programs will then be allowed to engage with the scientific community to build a research plan that they will consider. And that's where we are starting right now. Now is the beginning of this scoping study. Now is the time for all of us to come together and share our ideas and questions, the opportunities for science we see, the ability to inform decisions, and get this together so that we can create a plan that NASA will pick one of or neither of those 2. And then they'll set up a team that looks towards defining what the science will look like. And then there's a potential for up to a decade, more than $100 million of science. And this is resource that will come to the scientific community. We are not the people who will get this money, the people who are trying to coordinate. We're trying to do a service for all of us to bring drylands to the forefront, to bring the opportunities of science together. And as Ben said, looking at this timeline, I might not even be here by then. And so this is especially for the early career scientists. Get involved now. This could be yours. I was a graduate student when the large scale biosphere atmosphere LBA happened, and it was transformative in our understanding and supporting science, particularly of early career scientists like me. This could be that for our generation of early career scientists. So thinking about that. And that scoping study is meant to go as broadly into the scientific community as possible to identify what are the big questions, what's an initial study design, and what's the framework that we'll use to then take, and NASA will be able to evaluate proposals that build into that framework in the future if funded to do that science. But we want to get the big questions right now. We want to think about the research opportunities now so we can build that correct framework that will be so powerful moving forward as the larger program continues. And this is the group of us who have come together to suggest that the time for drylands is now, that this scoping study could do so much to improve our understanding and management of these systems, and also could feedback to improve remote sensing tools, because drylands offer those tools and the data interpretation for remote sensing a lot of challenges that will let us make those tools better. As I said, this isn't us getting the funding if this were able to move forward. We want to work with the scientific community to distill our best ideas, to figure out what we think the most important way forward is so that we can bring that to NASA and hopefully move it forward. I like that we're not only all passionate about drylands, but we represent lots of different types of institutions, multiple federal agencies, different universities, nonprofits. And I think that represents not only our desire for really exciting science, but to make that science useful and accessible, to put it into the hands of decision makers. So to think about what is the final step of that research? How do we build the kind of information that could make a difference, not only to all of us thinking about science, but to those of us working on management on the ground. So this was the straw dog that we created for the scoping study proposal, adaptation and response in drylands, ARID. And all of this is up for revision or even for totally complete change. We wanted to create something as a framework for joining our ideas. We wanted to give you all something to think about and to iterate on, but this is not the end. This is the beginning. And so we want to get all of your feedback through the next year of the scoping study to make this as powerful as possible. And I wanted to step you through it just so you could think about it as you continue to refine your own ideas. So one of the things we focused on were the drivers of change, things like that increased frequency and intensity of drought, changes to the timing of drought, changes to the temperatures that are occurring during drought. Just as one example, what are the things that are pushing these ecosystems towards their thresholds? Can we better quantify them? Can we better represent them in models? At the same time, thinking about how the ecosystems respond. This was an old growth pinyon juniper woodland that was on Ute Mountain Ute land just south of Mesa Verde National Park in southwestern Colorado. It is now an invasive exotic cheatgrass nightmare. We had done studies in this forest before the fire. There was not cheatgrass there before. Cheatgrass is now the dominant cover type. Pinyon juniper woodland used to be the dominant cover type in that area. It's now relatively rare because of the change to fire regimes and the increased frequency of stand replacing fire happening in the region because of believed aridification of fuels. How does that affect us and the services that we rely upon? Thinking about that food production we talked about, thinking about carbon sequestration. What are the consequences of these changes for the systems, not only in and of themselves, which is important, but for the way that we interact with those systems? And then how do we come up with adaptation, mitigation, and management solutions in the face of that change? And I think this focus on solutions is not only important because we have to find solutions. Now is the time to be hopeful, not Pollyanna, everything will fix itself, but to dig deep and to find that innovative way forward, but also for our mental health. It's hard being people who just study how in trouble ecosystems are on this planet. And so thinking about solutions is an important counterpoint to thinking about the problems, both of them being important. Some of the focal themes that we talked about during the preparation of the scoping study, things that you would expect. And my guess is that most of you would find yourself in these topics. Again, these are not the final topics, but thinking about carbon and water linkages, thinking about drought, thinking about attribution of carbon to different components of the system. How do we dive into the specifics of what we think the coolest, most relevant questions are in a way that will allow us to come up with a framework that is best suited towards enormous success? And I'm happy to share these slides with anyone who's interested. I love seeing people take photo. Take photo of any slide you want, but also I know these words are small and I'm happy to send them to people. We can use any tools we want. We know that remote sensing will be a part of this. It's a critical part of the field campaign itself, and it's NASA money. So we got to have satellites in there for sure, as well as other ways of remote sensing. We're particularly excited about drones right now and the potential for drone data to link with satellite data and airplane data to give us a different look at ecosystems, a different resolution. Numerical modeling will almost certainly be a critical component of this as well. How do we take what we're learning to scale in numerical space and to forecast into the future? Research networks like eddy covariance networks, long-term data and gradients, experiments, pushing the system and seeing what happens and better understanding those changes. And so what we're thinking some of our larger goals will be to improve our foundational understanding of drylands, to scale this understanding across space and time, to use and improve models to better understand and predict changes in the future, to improve the remote sensing toolkit in and of itself, and then to inform some of those management solutions. And one of the big ones to support the next generation of scientists in their important work. You all are the future. And so we want to be able to support you in that. The last thing that I want to say is this is going to be a global study. These dots represent eddy covariance towers globally, just as an example of the type of data that we could collect and synthesize and join with remote sensing data. We want to embrace the global network, and it's part of the mission of the Terrestrial Ecology Field Campaign, but there will also certainly be a focus on the United States because we have so many opportunities to assess drylands here. We have such incredible science and knowledge, those on the call, those in the room, and the way the funding structure works, we'll need to focus on the US in terms of how we can move money around to do this big, important science. But the global understanding is the larger mission. Okay, now is the time to be involved. We really want any thoughts and ideas. There's no wrong answer. We want to know what you're thinking, and please think about talking about ARID in your talks or to your NASA program managers or to people. If they hear from you that this is something you could see yourself in, or this is something that you think could be important, it will make a difference in their consideration of what the most powerful way forward is. So please don't hesitate to think about that. The 1 year starts now. We'll be doing sessions like this one where we'll share ideas. We'll be refining framework or potentially revising it and then getting more comments on that. And then we'll write a crazy long report to NASA about what we found and what we think the best way forward is. And we'll ask for feedback at all the stages and throughout. This is a way you can sign up. Tell us a little bit about yourself. If you want to take a picture of this, like I said, I can share the slides. You can also just email me or Bill or Florine or anyone from that you know from the committee heads, and we'll be able to get you on the list so that we're keeping you apprised of what's going on. But I think the main take home is this is a really special opportunity. I think probably a once in a lifetime type opportunity to be a part of pushing such big science, $100 million in 10 years. And, the types of questions that we can ask, the types of goals that we can have are really different with that kind of project. So we very much hope you'll be involved. That's the way it's going to be awesome. That's it. Oh. Okay, so next up we have Steve running one of the most amazing remote sensors on this planet. Steve has been transformational in our understanding of remote sensing tools and how it can help us understand the biosphere. He really took his eco-physiological beginnings. I think I've seen a picture of him with a lichor on a leaf. And before lichor, what was it? Oh, nice. Yeah. Times were tough. And he recognized the importance of scaling that we're talking about today and was able to really lean into the tools of remote sensing and bringing ecosystem function and physiology and organismal response into the remote sensing realm in a way that I have not seen anywhere else. He also personally affected my love of remote sensing when I was a postdoc at the University of Montana. He is won so many awards for his science, including a Nobel for his work in the Intergovernmental Panel on Climate Change and our better understanding of this changing planet. Please help me in welcoming Dr. Steve Running to the stand.
Yeah, this is a little bit unnerving to know that there's 197 people on the Zoom. And I have to watch out what I say, that I might use somebody's name in vain, not knowing they're listening, like Tucker, for example. I've been to U of A here lots of times over the years. This has really been a magnet of earth science for decades. But I hadn't been here for 6 or 7 years now. Have you noticed there's little robotic coolers riding around? Yeah. Okay, I've heard that you can text somewhere, and if you're feeling you need a little boost, you can order a bunch of margaritas and they show up. And so anybody who's a local here, why don't you give that a try? See if you can schedule margaritas for the house at about a half hour from now and see if they show up. This wasn't around anywhere else I've ever been. Yeah, history talks are, I guess, about all somebody my age is good for anymore. But I hope to actually turn my history into something useful for this project, because my original training was in tree water stress physiology, and so I've been working on arid lands and water limited ecosystems my whole career. Now, one of the things that I find quite interesting in watching this morning, this arid land scoping is way different than those other field campaigns. And it's way different in the critical aspect that it appears that NASA really wants to make the final connection, the final mile to land management use. And none of those other experiments, it was all just doing science. And none of Boreas and LBA, I don't remember any effort to be connecting to a final land management user community. So that is an important additional step that I hope the stakeholders that are here recognize how critical they are. NASA doesn't manage any land except Cape Canaveral, I suppose. And so they don't know what the real issues are out on the landscape. And as I'll illustrate pretty quickly here, when we started, there was no data, but now there's just petabytes of data everywhere. And now the issue is much more, how do we get through the petabytes of data to distill it to information and then deliver it in a way that it's usable? And I think for NASA to take that additional step of connecting with the arid land managers makes this really a quite remarkable opportunity. And I hope the stakeholders stay engaged, because without them, the rocket scientists won't get it right. They'll end up with these esoteric variables that you've never heard of, and things like bidirectional reflectance distribution functions and things like that. And you'll go, what? We have a mine reclamation to work on. And so that's an important part of this scoping that I hope everybody really steps up to. And with that as a preamble, and with, I think the margarita is on the way. See, if you talk too long, the computer hibernates. And then it doesn't know it's supposed to keep going. There we go. And okay, yeah, so just you wanted history, you're asking for it. This was me doing my master's thesis work on stomatal conductance in conifers in 1973. This was before LICOR even existed. And so people made their own instruments at the time. And what I find interesting now is back then we never worried about policy relevance. We never worried about our science being on the front page of the New York Times. We just innocently were trying to understand our system. Same thing, my PhD work in 1978 and 79 in Colorado. This is the cuvette that Paul Jarvis's lab built for me to work on. Again, LICOR didn't even exist yet. And this was some of the first field measurements of gas exchange back at the time. And so we're so far ahead now. It's kind of amazing sometimes when I look backwards. So I was a physiologist by training, but was doing some early computer modeling. And I was invited to work to be part of some scoping studies at NASA headquarters called Global Habitability in 1981 is when we started. And I met Jim Tucker. And of course, back then, he was the one that figured, we've got a weather satellite up there, AVHRR. Can it tell us anything about the land surface? And really, nobody else tried that I know of except him. And so I was working on my computer models of daily transpiration and photosynthesis, what started as Forest BGC and became Biome BGC. And I was on sabbatical in Australia, and I contacted Jim, I don't remember details, about getting one of these new NDVI data sets that he had. And so he sent it to me. He had to mailed it, snail mailed me a floppy disk, because that's all, there was no other way. So he must have mailed me a floppy disk of NDVI of a set of these test sites that I was playing with my model on. This turned out to be Madison, Wisconsin. And I still remember to this day, this was the one aha moment of my entire career, is I dutifully loaded on his NDVI data set and did the scaling to match it with my photosynthesis and transpiration calculations. And I pushed the graph and up came this. And I just went, it's hard for you to remember or not realize how little we knew about what NDVI actually meant back then. This is before theoretical analyses like Pierre Sellers did. And so it was really quite a black box. And when I saw that this NDVI black box was basically tracking the seasonality of photosynthesis and transpiration in this Madison forest without any other information, just on its own, I was just incredulous. And I right there figured, boy, this NDVI is something that's worth figuring out. And so that's how I got into this deal. It didn't work that well everywhere. Here's my hometown, Missoula, Montana. And you started seeing then that, okay, this remote sensing gets fooled by snowpack. When there's still snow on the ground, the NDVI doesn't go up, even if the trees might be waking up. It didn't do very well at summertime water stress. And so, which is of course highly relevant to what we're talking about here. And so the first graph got me interested that NDVI was worth pursuing. And then some of the next analyses started reminding me how much we had to figure out to make it valuable. And of course, here's his immortal cover of Science magazine, 1985. And it's hard for people to imagine now that before this, we'd never seen the whole world. Literally, we'd never seen the whole world all at once. And to see an image of an entire continent was something just unprecedented at the time. And so this is where we started in. Of course, Jim's going to tell you a lot about what he did here next. But this is where we started into the land remote sensing is in the early 1980s. Now, because I never had any training in remote sensing to this day, I've never had a class in remote sensing. I thought of it that the normal remote sensing people saw these new data sets as basically a digital aerial photograph. And so they saw the digital image as their final product of interest. And for some reason, I just didn't think of it that way. I thought of it as another geospatial data stream that I could use to drive more complicated models of the system. And so this was in this global habitability document in 1983. And it's hard for you to see because this is so old, but basically here's where the NDVI came in estimating leaf area index. And this was being integrated with surface meteorology to drive a photosynthesis model, to drive components of a carbon budget. Nobody ever thought of using remote sensing that way back then. Now everybody does it, but back then, really the remote sensing was just a digital image, and that was the final product. And so with that kind of warm up of ideas for advanced use of NDVI data set proposed to the Modus Science team successfully. The planning document was came out in 1986. The funding started in 1990, our selection to the science team, and our first launch was just short of 2000. And so when you think of these kind of big projects, you got to be in it for the long haul. These aren't overnight projects. The bigger the money, the longer the gestation time is a principle of NASA funding, probably of any agency funding. And when I think of this arid land planning, this is going to take a good long time to plan, but hopefully the payoff will be a quite extended period of science. So I was able to test this idea of using satellite data as an input to a complex model with this regional ecosystem simulation mode. Yeah, this was my IBM XT that we ran at the time. And this is 1,200 square kilometers of complex landscape in Montana that we did this first leaf area index map, daily evapotranspiration for the year, and then daily photosynthesis. This is the first color image ever printed by the journal Ecology. You go look it up, 1989. And so this at the time, nobody'd seen things like this before at all, and nobody'd really even thought of using remote sensing that way. Of course, this is what we can now do with the same landscape, this or better. So in today's world, we can do a digital analysis of things like daily carbon budgets, daily water balance to very high resolution. But when you have to start thinking globally, the first thing I learned, and you recognize I started with this training in leaf scale gas exchange, how do you go global? We had 120 million square kilometers that we had to compute every day. And so that was the marching orders for this, our level 4 daily GPP annual NPP data product for MODIS. And so the first thing I did was say, we actually know a lot more about global climatology than we do about global ecosystems back then. So I thought, let's start by first just parsing out the most simple climatic controls of a plant's leaf gas exchange, and basically boiling it down to sunlight, temperature, and water. And of course, the sunlight, you know, you think back to what, junior high in biology, and you learn how sunlight drives photosynthesis. Same with temperature. You learn that the basic temperature response surface for leaf gas exchange. Water was the tricky one, and to this day, so here we are talking about water limited ecosystems here in 2023. And it turned out that as we mapped this, you could, and I think a couple of our earlier graphs have shown how much of the Earth's surface is fundamentally more water limited than any other primary constraint. And so if you don't get the water limitation right, you're a goner already for a good half of the vegetated land surface. So in thinking through this this sort of simplified version of controls, you could come up with this kind of effective growing season. You might even call it potential growing season. And so this was what this looked like. This we were doing by the early 90s, I think, as we started to lay out our algorithm. And to look more specifically at how this then separates parts of the world, we did a color-coded mapping of a seasonality for a boreal forest, like you might find in Russia or Canada, and then an arid African savanna. And the color coding kind of says it all, that when you're at high latitudes, your first limitation is it's pitch dark there all winter long. And so you're first just getting your day length coming back. But as you come into the spring, it's still below freezing. It's still cold as hell. And then so until you got through your light limitation and temperature limitation, then finally your ecosystem wakes up. And it goes through its growing season until on the other end, those things crash back down like we have this time of year. Contrast that with subtropical, like as an example, African savanna. It's never light limited because it's near the equator. It's never temperature limited because it never gets cold. It's all about water limit seasonality. And so this is the sort of fundamentals I tried to build into the Modus daily GPP logic. And notice I haven't even done any physiology yet, given that that was my background, but I saw this was the only way we could ever get global. Now, this is where particularly I think it's worth us thinking through for this arid land project. It's always been clear to me that to understand the water limitations on your ecosystem, you've got to understand the whole water balance, not just the input precipitation, but the input precipitation, the storage, soil, and sometimes plant storage, and then finally the outflow, either stream outflow or evaporative demand. And so I would think of this as a land water balance, as I called it. And I imagine from year to year, as we have wet years and dry years, which are absolutely natural even before climate change came along. This is a slide I made 20 years ago, is when the water balance was decreasing. These are all the things that would be triggered and accelerated by a decreasing water balance. And on wet years, these are all the things that would be increasing. And I've tried to get this kind of holistic picture of this year-to-year variability of the system in water balance. And I think as you contemplate an arid land project, you're going to be all around this kind of thinking somehow or other, because it really is what the system does in its year-to-year variability. It's more water limited than any of the other fundamental constraints by far. And you got to get this right, or you're not going to get arid lands right. And so we had, as a companion to our daily gross primary production algorithm in Modus, we also had what was known as mod 16, the daily evapotranspiration. Now, it's interesting I can confess to you now that when I proposed in 1989, I proposed both ET and GPP together. I was given instructions quite clearly by headquarters after I was selected that they were way more interested in the carbon variable GPP, and that I was to prioritize that and basically put ET on the back burner until you get around to it. And at the time, I just thought, okay, you're writing the checks. That's what I got to do. But as I think back now, we really needed to bring ET along concurrently with GPP, because you're never going to get the carbon cycle right in arid lands unless you get the water cycle right, is basically my message. And of course, one of the first things we worked on is looking at interannual variability. And so this is just a look from a good while ago of year-to-year variability of wet and dry years in terms of annual evapotranspiration for North America. And of course, there's no surprise to any of us, there's lots of year-to-year variability. So this is really just quantifying what we intuitively already knew and what you're going to want to be doing in an arid lands project. But then kind of almost for fun in our spare time, we started paying attention to the MODIS land surface temperature. And this is part of what I want to talk about with this group here today. The MODIS LST was developed by an engineer, Xingming Wan, and he did a good job of writing an algorithm and building a validation program, but he didn't seem to have any idea of any kind of science question to ask with it. And so we, I guess, with my interest in arid lands, we got kind of curious about looking at this the land surface temperature data set. And actually, it started when I was in China, and they took me to this place called the Flaming Mountain, and it had a sign saying it was the hottest place on earth. And I go, how do you know? And I realized, wait a minute, our MODIS LST maps the whole world every day. I'm going to go home and see if it's the hottest place on earth. Well, this is about 6 years worth of our, every year we would put out a press release. I mean, this wasn't high-powered theoretical science. NASA never gave me a dime to do any of the LST work, even though we got a half a dozen journal papers out of it. But it was, the press loved it, because where's the hottest place on earth? And one time it was Australia. One time it was pretty close to that flaming desert in China. But you know who won year after year after year? The juggernaut was a place called the Lut Desert in Iran. And when I think it was the New York Times was writing a little piece on this, as I say, we got tons of press for this, even though it wasn't big science. And recognize these are radiometric surface temperatures. These are not air temperature, which is what we always normally see. And so look at the numbers, 70 degrees centigrade. Now, believe it or not, there's probably surfaces right out here that hit 70 degrees centigrade in midsummer. And well, it turns out these Iranian scientists emailed me and they said, dear Dr. Running, we see that you found the Lut Desert, the hottest place on earth. Would you like to see a picture of it? Would I? Now, you want to talk about arid land science, or don't you? This is the Lut Desert. Oh, yeah. See, here's Flaming Mountain in 2004. They put me on this camel for a photo op. But serious arid lands, there is not a chloroplast in sight as far as the eye can see. But recognize that this is only the extreme. The point, the bigger point for the work you're trying to plan now is I find using radiometric surface temperature could be a really valuable component of the science you do. And you know, the thermal imaging, the sensors were just fine, but the overpass time has never been optimal. To this day, it's never been optimal. When they put LST, the thermal imager on Landsat, and of course it goes over at what, 9:30 in the morning. That's the worst time of day. That's the last time of day I want to see the LST. The WMO decades ago figured the most valuable temperatures of the day are what? The highest temperature of the afternoon and the lowest temperature at night. And those two things really drive both afternoon potential of evapotranspiration, and of course at night particularly, it's defining your growing season in terms of freezing temperatures. And yet we never had satellites going over the right time. Even though the sensors are wonderful, they're going over the wrong time. And I argued endlessly for this at NASA headquarters. And this illustrates how little clout I have at NASA headquarters. They never did anything about it. Now we do have, and I'll get to this in a minute, geostationary, that I really think could be a big component. Because what we found when we started playing around with this unfunded LST science is you can see it in a way, it kind of magnifies your look of the land surface, particularly the land surface energy budget. In a way, it's your closest thing to seeing the energy partitioning of this surface in terms of evaporation or increasing temperature. So like looking at the sub-Saharan Africa, you would see on the edge of the desert, you would see an LST of 60 degrees all the time, almost every day. And yet not very many 100 kilometers into the rainforest there, like in the Congo Basin, the highest temperature we ever saw was 35 degrees. And boy, does that tell you something about how vegetation moderates the energy budget of the system or what. And so to me, as you talk about an arid land science project, I think back to particularly paying attention again now to LST related to whatever NDVI or VI spectral index you want, because it turns out it gives you a whole bunch of information that you really can't see those kind of energy budget components otherwise. And so this was a place in Oregon where there were irrigated poplar right next to the Columbia River, right next to sagebrush. And look at the difference in radiometric surface temperature, 60 degrees to 33 degrees. And so here again, this is giving you a look at your plant canopies from an energy budget point of view, not simply from an optical point of view. And I think it can be, for arid lands, a really important part of your monitoring. So we back then, this was, geez, I can't remember, 1987 or something, we came up with this clustering of different biome types in an NDVI versus surface temperature two-dimensional space. And then we looked at that and tried to put together first a drought index and got the cover of BAMS. That's the only time we ever got the cover of BAMS with this drought severity index. But then thinking more, I guess, conceptually, and this ended up on the cover of Ecological Applications. We thought through here again, this NDVI versus surface temperature, but thinking of the seasonal hysteresis loop these different biomes would go through, and I won't crawl you through all the details here, other than to make the point that everybody pays attention to NDVI. Almost nobody does much with surface temperature to this day, as best as I can see, and yet there's a whole bunch of latent monitoring capability for arid lands that I think this project should really work at exploiting. This, we came up with using this same logic for this global automated disturbance index, because I think, and here again, coming back to this arid lands project, probably one of the first things you've got to get right is basic change detection of the system from year to year. And you got to automate it. You can't be doing this by hand, pixel by pixel. And so this is what we were working at the time is, here it's basically the same sort of logic of ratioing the land surface temperature against a vegetation index and seeing how a wildfire would trigger a big positive spike. Irrigation would trigger a big negative spike. Both of those are disturbances, quote unquote, by the standards you think of with a natural system and trying to come up with an automated way of doing this change detection, because you got to get this change detection right. Nowadays, there's so many different satellites, and in today's world, UAVs, there's lots of different ways of doing it, or different platforms. But I think a logic that makes use of this surface temperature is going to be a valuable part of it. And so then we would do things like a monthly disturbance index over the US through the summer, and seeing how the drought impacts would really explode as you got into the summertime. And the current drought monitor doesn't use any of this at all, of course, and this is one of the illustrations of where interesting research theory doesn't necessarily ever get into practice. And probably nowadays, there's probably better ways of doing this than what we did back then. But I'm hoping it's illustrating that LST is a measurement that is right at our fingertips, and I don't think is used very well yet. So I gave a talk at Princeton. It was actually in 2016. And I said at the time, boy, this new GOES is going to then, for the continental US, give us minute by minute LSTs night and day. And if I hadn't been retiring, I think that's the next thing I would have gone and had some fun with, is looking at that diurnal measure of LST that GOES now gets. You know, the older GOES satellites were radiometrically nowhere near rigorous enough for our kind of science, but the new ones, it's a different story. And I think I think Paul Stoy sent an email just a week ago saying something similar, that this is something that we should be paying attention to, is the next this new, well, it isn't new anymore. It's been for years, but this is something that I don't think in the NASA TE we've spent nearly enough time on, with the geostationary, partly because you don't get a full global data set. But since this is aimed primarily at the Southwest US, you could do a lot with that. And so we recognize that there's new extremes happening that we never thought possible. This is that big heat wave of the Pacific Northwest. I grew up in Seattle, and it used to be front page headlines when the summer temperature went above 80 degrees. We got excited. And so the thought that it hit 108, are you kidding me? Portland, 116. This is Sahara Desert sort of temperatures. The real point is climate change is pushing our system beyond what we thought was possible. And it's our job first to monitor these anomalies, but then secondly, to understand them, and third, to try to be ready to be resilient to get through these sort of anomalous conditions. And I think in arid lands, it's particularly the case, where we've got very water limited systems that I think, as it's already been pointed out, have huge interannual variability that we, number one, need to monitor accurately, and we have the raw capability now to do so. And then number two, understand the dynamics that we then monitor. And now with this project, try to be feeding information to the land managers that are trying to react to this. And that, I think, is a very interesting part of this project scoping. And so my last slide is, this is the way I've had many of my GCM colleagues in talking to the press about climate change, and they try to, beyond talking about 1.5 degree sort of things, they'll say something like this: well, the wet regions are going to get wetter and the dry regions are going to get drier. Well, you know what? The public, that sounds like you're contradicting yourself. And so you really have to think and then explain your way through that. We know the air temperature is getting higher. And as long as you're over, that air is over a wet surface, it's going to evaporate and hold more of that water vapor in the atmosphere. And that'll bring clouds that'll make the wet regions rain more. But if that air is over a dry system, that air is going to get hotter, but there isn't any water to evaporate. And so then the dry regions are going to get drier. And this is the sort of thing we have to, number one, monitor accurately, number two, understand theoretically, and then number three, be working on how we manage towards these sort of issues in the future. And so I find this arid land project scoping to be a very interesting challenge. I hope NASA really is set to go through with this, because I think it is a huge part of the land surface. And as we've seen with other slides, it's a fundamentally important landscape globally, and it really hasn't been studied in to this level yet. And so, but I do want to warn you that these sort of plans, like I think that I started working with NASA in 1981, and it took till 1999 for the Terra platform to go up. So you kind of have to have the long view. In a way, it's a bit of a career gamble, I recognize, to put into these sort of planning. But what it does do on the other side is allow you to do some big science that hopefully will really improve arid land management directly in the future. So that's it. That's all for me.
And yeah, it's great. It's great to have Jim Tucker joining us. He's joining us from the hospital, unfortunately, but as we said earlier, he feels so strongly about this campaign and drylands that he's willing to join us. So we very much appreciate that, Jim. Jim, I think we all in the remote sensing community know very well. Steve gave great slides to highlight some of the amazing contributions Jim has made. Just a giant in the remote sensing field, starting with the discovery really of normalized difference vegetation index, still one of the most widest used indexes that we use in the remote sensing community. An amazing contribution that was originally developed in dryland systems. I'll plug also some of the first estimates of deforestation. Jim was a key part of, and what I think is one of the coolest things is that science cover that Steve shared of NDVI, some of the first large scale maps. And now today, Jim's going to be talking about some of his latest work, which was on the cover of Nature, right? In 2023. So 1988 to 2023, cover science to cover of Nature, with a ton of amazing accomplishments in between. So with that, we will turn it over to Jim. Hope this goes smooth. Thank you so much, Jim.
Okay, Jim, we're going to try this. Take it away.
I apologize to everyone for the difficulties in projecting.
Jim, I think if you can mute the sound on your end. There's no mute. Just so sorry for this technology, Jim. Okay, let's try that again.
Okay, I would like to thank Steve Running for being a great warm-up act. Steve and I always work well together. I'm always happy to be his warm-up act as well. So the first slide, which I'll show, is an anticipation of what we might be doing. I've been assembling all of the Maxar data of arid and semi-arid lands. And recently, my coworkers and I published a paper on 10 million square kilometers across Africa. I'll show some of those results and methods. But we also can get all its data for the southwestern states and much further north than what's shown on the left-hand side of the figure. We can then make comparisons if we need to in terms of tree and bit mapping. in all of these areas, which are indicated by these large blocks of red color, including Australia. Next slide, please. In the paper I show, these are all the people who took part in it. We had a lot of fun. It took a hell of a long time. This is a paper we published the proof of concept on in October of 2020. And then we immediately started work on answer of this. We submitted the paper I'll describe right now and summarize ever so briefly in January of 2021, and then we spent a year revising it as we had to wait some of the reviewers and a few other things. Okay, so these are all the people who took part in it. We had a hell of a lot of fun, and I've enjoyed working greatly with all these people, especially with Martin Brandt here, and our area. I'll explain more as I did. Next slide, please. Okay, so this is the paper in Nature, and in it we write, or I wrote in the acknowledgments that the first four authors, Dr. Brandt, Erno, and Guerrera, should all be considered as the first authors because of fundamental contributions to the paper. We had a lot of other people as well. This is the area which we covered in our paper. We worked from the zero precipitation per year area on the south side of the Sahara, all the way down to 1,000 millimeters on the bottom. And you see here, we mapped tree crowns and we converted them into carbon at tree level. Next slide. This is extended data 10. It's a summary of the whole paper. We used a large volume of commercial satellite data, a third of a million images. We then formed them into a mosaic. And the mosaic which we formed was an array of 40 trillion elements. So when you work with commercial satellite data, you end up using or utilizing very, very large arrays. Ancient Guerrera wrote our combinational neural net unit code. There are many aspects of the hyperparameters that can be found in our proof of concept paper. We use that for the processing. Martin Brandt, then next, we drop down in the boxes on the left. So the third one, Martin Brandt single-handedly selected 89,000 trees as training data. And the machine learning, the learning part is training data. And then I was able to get unlimited high-performance computing on the Blue Waters, University of Illinois machine. When it was new, maybe 8 or 10 years ago, it was the fifth fastest supercomputer in the world. The great thing about Blue Waters, it had a hell of a lot of processors, but it had 26 petabytes of disk storage with transfer rate of more than 1 terabyte per second from core to disk or disk core. And we threw all these things together and sort of ripped it through, and we mapped 10 billion tree crowns. So we were mapping tree crowns. Let me have the next slide, please. And then converted the tree crowns into carbon by using allometry. Now we had no other choice. If we would have had the heights of all of our 10 billion trees, it would have used that and we would have done much better. So we used allometry, and the allometry is the source of more than 95% of our uncertainty. And the allometry provided us to make an estimate of the wood carbon, of the tree wood carbon, and leaf carbon, all at the tree level, with an uncertainty of plus or minus 20%. And then we put ourselves into the stockade because we had 10 billion trees, and how the hell should anyone use them? Because you have 10 billion items that are not well organized. So 2 members of our team wrote a series that enables you to look from tree 1 to tree 10 billion. I'll show 1 or 2 examples to the end. So this is what we did. Now let's go see some of the results. Next slide. So we had our proof of concept paper in October of 2020. That was Martin Brandt, Tucker, and other authors. Then we had our carbon paper in March of 2023 that was Tucker Bratt et al. And we used a third of a million lifestyle images. We actually mapped 10 billion tree crowns, and though we converted 10 billion of those in the carbon because they were in the semi-arid area where our aerometry came from. We also mapped 1.6 billion bushes, which we have done nothing with. They have crown areas of 1 square meter to 2.75 square meters of area. And we hope to have a follow-on paper using 2 dates, an earlier date and a later date for the same area as our more recent paper. Next slide. Okay, we're on the south side of the Sahara. It is in the Sahelian Sudan zone. It has a monomodal rain season. The bottom figure is a MODIS NDVI plot. As Steve Running said, MODIS is a phenomenal instrument. And what we see in the dark and the very dark black line is the mean. These are 20 years of data. And the green area is the envelope of the minimum and the maximum of values over these 20 years of observation. So 1 30 degree by 30 degree cell, which you see at the bottom image on the upper right-hand side of that. And the top of this picture, what things look like in the rainy season. In the dry season, in the early dry season, the trees remain green, but their herbaceous vegetation dry. Next slide. So Steve showed a few slides of him, and here's the slide of me on the far right, although it looks like it's blocked out. But I started working in Sahelian Africa in Senegal in 81 and 82 and 83, using 8-kilometer data and 1 kilometer data. And I never dreamed I would ever be able to use 50 centimeter data in the same area. Next slide. Now, this is really interesting, I think. On the left-hand side is an NDVI image of a tree crown. It has a total crown area of 9 square meters, crown diameter of 3.4 meters. And on the pixels, each of those pixels are 50 centimeters by 50 centimeters. You see the NDVI on the left, these are digital globe maxar data. And on the right, you see the panchromatic bands, and you see the associated shadow. So we define a tree as something which has an NDVI canopy with a screen and has an associated shadow. And has to have an area of at least 3 square meters. Next slide. Now, here's a slide which our colleague Ines Fung refers to as a flying carpet slide. This is for one particular tree with a crown area of 14.75 square meters. This is because we're using 50 centimeter data. For aerially, this means we're using a very large amount of quarter square meter pixels. And you see as NDVI green, and you see the associated shadow. The arrow and on the right-hand side in the band points to the tree. And below it, and the NDVI image, the arrow points to this particular tree. And the crown diameter of this particular tree, if you assume circularity, would be 4.3 meters. Next slide. Martin Brandt sent me this picture. He was in the field, and he said, Jim, people who think that we're hanging by numbers as a very noted ecologist accused me when I was working with Steve Running and global habitability making images of Africa. This is a tree crown where Martin Brandt puts a picture, and we have co-registered that to the tree with the arrow in the gray area. So you get an idea, we don't map all of these grass prospects. They don't have pronounced shadows. And we largely, overwhelmingly don't map them. And this is one example of how we can ignore traffic and bushes and only focus on trees. Next slide. Okay, so I mentioned we also mapped 1.6 billion bush ground. So this is something which we haven't utilized yet, which we could, and this could be very useful in ARID, where we can extend our mapping with this data down to the 1 square meter crown area for bushes, because we know bushes are really important. Next slide. Now, what about our uncertainty? So when you perform a study like this, you have to spend a lot of time on your uncertainty, or also referees of deep rock. So the lead editor of Nature returned our paper after we submitted it in late December of 2021, almost 2 years ago, and said, Jim, you have to have a better uncertainty analysis. So the first thing we checked was the uncertainty analysis for how accurately we map crown area. Now, the only way to do this is to have 1 or 2 people go in and very accurately map the pre-crown area, and then run our neural net, map the 3 crowns, and compare the areas of the hand-delineated crown in red to what the neural net mapped. And we found a crown area error of 2.5%. So this error is plus or minus 2.5%. And then next slide. So now we go to omission and commission error. Omission errors are when there's a tree which you don't map, and commission is an error when there's something you call a tree and it's not. So 10 of us, or maybe about 8 of us in the group did this. I led this analysis. I felt if I was going to be the first author, I damn well better go through everything, because you're always worried about things that haven't happened, and it's good to tie things down. So what we found was the difference of the omission and commission errors was 2.2%, and so that was our overall error in terms of omission and commission errors. Next slide. When you work with satellite data, you have opportunities to make Christmas cards, Hanukkah cards, good solstice cards, and Happy New Year cards. This is one image which I analyzed for omission and commission errors. In the lower left-hand corner, under the annotation omitted tree, is 1 tree that was missed. That was the only error out of 67 trees that were mapped in this image. We all were very impressed by the power of convolution with very, very accurate training data. This is another I use when you work with satellite data. If you can rig the colors so it's festive, it makes your own Christmas cards. Next slide. And this is one area where I thought we were going to have a lot of problems. That was with burn scars. So what we did was we analyzed a large number of images, which were 256 meters or 512 pixels by 256 pixels. This is one of them. And in this image, which we processed with our neural net, which the dark areas are a burn scar. And I thought these are the areas where things could be really screwed up. We were very pleasantly surprised this wasn't the case. The burn scar removed all the grasses and all the bushes because they're not fire sensitive the way trees are. And here we only had 4 areas out of 150 trees we mapped. And area number 1, there were 2 trees which were omitted. And then below area number 2, there's a weird sort of cheese slice something which was mapped a tree, which was a clear error. And then in area 4, there were 3 trees and not 2, so there's 1 error there. So overall, we had 4 errors, and I never thought of burn scars as being friendly to what you were doing, but in terms of mapping 2 crowns, this may be the case. Next slide. Okay, this is a summary of what we're doing. So we want to go to tree carbon. First of all, we have trees in the landscape. We then image them using Maxar high spatial resolution satellite data. You can see the tree crowns at the panchromatic image in the middle. You can see the tree crown and you can see the associated shadow. And then that's what we use in our neural net to very accurately map trees by deep learning crown size using an extremely large learning set of data, 89,000 heroically selected by Martin Batt. Next slide. Here's the alarmetry, which is the overall dominant by probably 95% or 99% of our air going from tree crowns to wood, leaf, and leaf cup. You'll note immediately we don't have these parametric values for tree crowns and roots. I think we all understand the reason, and I'll throw a slide to emphasize that. For wood, we had 600 individual allometric crown areas where the wood was measured, the tree was cut down, all the branches were stripped of leaves, the leaves were dried to get the leaf area, and then the wood and the branches were dried to get the wood mass. And on the far right, you have the trees where we had 900 samples, or excuse me, on the far right, so the leaves, we had 900 trees. The trees were cut down, the crown area was measured before they were cut down. And then we, or the elementary team and the knows, stripped off the leaves and then dried them. And then that's where we have our dry leaf mass from. Next slide. This is why getting root mass. When I was a graduate student in the grassland biome as a pony intensive site, one day I got volunteered to work on below ground biomass in a herbaceous system. And that convinced me I never wanted to do that again. So I have great sympathy for all of these root people on here and those team. Here they're cutting down a tree in the upper left-hand corner. So they measure the crown area. They then cut it down. Now they will strip all the leaves off and weigh the leaves. They'll take all the branches and cut them and dry them for the wood mass. And this particular tree has a taproot, so they have to dig out the taproot and weigh that to get the carbon in the root. So this is laborious work. Next slide. Oh, geez. I think it's time to go to presentation 2.
We're opening presentation 2. Good job, Bill.
In case you're wondering, I'm in the hospital because of a staph infection in the finger. They just kind of took off on Wednesday last week. And when I showed it to my physician, he said, you have to get into the emergency room immediately and have it taken care of, or you could be in a very, very serious situation. So I think I take tomorrow. I only have, I think, 4 more IV antibody drips to go through, but I'd rather be conservative and do whatever they say. And so I'm staying here for that.
Well, we're so glad that you're doing better. We've been worried about you and sending good healing vibes. So definitely take all your medicine.
Well, okay, so this slide you've already seen. Let's go to the next slide. So let's go to the next slide.
Bill's working on it.
Oh, okay. And we'll go, yeah, okay. This is just a summary of the uncertainty analysis. The overwhelming error came from the allometry, and our total error was plus or minus 20%. Now, this assumes the independence of all sources, and we know that the wood mass and the root mass are highly correlated. What we did was we used 26 different species, and we merged everything in terms of our allometry because we had no basis for being able to discriminate the species or even the genus of the various trees. So our uncertainty analysis is conservative because of we did not include the variation of wood carbon and root carbon. Next slide. And then we started comparing our data to other things. This is a representation for our study area of the milligrams of carbon per hectare and wood, roots, and leaves. You see the leaves are very minor. Leaves are a low value, and wood is dominant value of spectrum rainfall. And the hyper-arid, arid, semi-arid, and subhuman areas. On the right-hand side is the average megagrams of carbon per tree. You multiply the megagrams of carbon per tree in this graph times 1,000, and you have the kilograms of carbon in individual trees. And you see our four zones. Let's go to the next slide. If we make comparisons, it's an interesting figure. On the left-hand side, we have the carbon probability distribution function. You see our area was an area about very close to the size of the United States, continental 48 states and Alaska. And we were able to map under 10 billion tree crowns and converted them into carbon, which totaled 0.84 petagrams. And on the left-hand side, with respect to rainfall, the probability distribution function of tree carbon, we're replacing this figure with a more easy to understand figure. And this is what we have in the paper. On the top of this figure, just below the top figure, horizontal line, you see the amount of carbon in each of these areas. It's very low in the hyper-arid and arid areas. It picks up in the semi-arid and the subhumid areas. And below that, in blue, we have the area of our study. So from 30% of our study, we have 90% of our carbon. And then on the right-hand side in blue is just a cumulative histogram of the total number of trees, the sort of cold snake plot. And then in the whatever type of plot or tree is in state in terms of color between the green and the black. That is the cumulative distribution of carbon with respect to tree crown. What we see immediately is if you want to get an accurate carbon density, if you use, you have to be able to measure tree crowns at a so small, which have a diameter of 4 meters, because that is about 15 square meters of area. You can use planet data, you can't get output data for this. And then it's even more pronounced if you want to look at carbon. In our study areas in which you use Sentinel-2, you would probably miss 50% of the carbon just because the individual trees is so small. Next figure. Now we compared our data to different estimates in the same area by many of our friends and colleagues. Those at the bottom, our data in the left-hand side of the figure are plotted within a gray zone. Our data plus or minus one standard deviation. And these are the mean values. And you'll see that some of the data agree with our data, every time our study is shown. And then it's just a total, this is just the background data. Let's go to the next slide. Now, when we get into some plots where we're only looking at above ground carbon, and this is what the actual plots look like. So the point of this is if you only deal with the minutes. Okay. So we deal with these values, and then you plot up how the data are actually plotted. You get a very different representation. So this, on the left-hand side, it's just the mean values, where you see certain of the studies that agree with our data on the in terms of mean values. When you look at these distributions, you'll see that our data differ wildly in terms of actual values from all of the others. Look at the next slide. Now we compare our data, which you've already seen in A. Now we compare them in C to the 20 models. And we see the mean of all the 20 models is the black line at the bottom. And it's just -1 centimeter. You can see we have no correspondence to any of the 20 models. And let's go to the next slide and let's see why. This is because the 3D models rely on force fraction in order to be accurate. And this is the wide range of force fraction. There hasn't been any way to estimate this over large areas, but now there are. And so I'm sure they will improve as a consequence of our work. Next slide. Then you also have to compare data in terms of spatial coherence among different estimates, because you could possibly get the means correct and the distribution correct, but you have to see how the actual areas compare. And that is the purpose of this figure. Next slide. Okay, so we started with our machine learning 3-crown output. We converted that into carbon at the 3 level, and then aggregate that to carbon at the hectare level. And then we combine everything. And it's the Oak Ridge National DAC. We have all of our tree carbon data. We also have all of our tree carbon data in our viewer, which people can go to the methods section and look around. If you need to fall asleep at night, you can certainly do that. And you can access our data for thousands, if not millions of trees as we so desire. Next slide. In some areas where there's been an appreciable increase in the amount of carbon stored, here's an area in Senegal from 2002 on the left and 2021 on the right, where the total carbon increase has increased from 6 megagrams per hectare to 10 megagrams per hectare. So there's a great potential for looking at variation in tree carbon and to scale of individual trees using these mapped data. The next slide. And this is a really important figure. So we started with 30 million molecular satellite images. We covered an area of 90 million square kilometers. Now, if you were to buy these data for $1 per square kilometer, that would be a $90 million data purchase. And we all know this is impossible for all of us. We all operate close to the poverty line when it comes to projects and buying things. So what we had to do, we had to use the early dry season to maximize our tree crown mapping. Otherwise, trees would lose their leaves. If you would get it to February and March, and your tree crown mapping accuracy would be great. So our data selection was not based upon year, it was based upon month. It's a high preference for the early dry season of November, December, and January. So if you look in C and D on the bottom, you see we have more or less the same distribution of data which we use by year from 2002 through 2020. But in terms of months, we managed to concentrate more than 90% of our data into the months of November, December, and January, the 3 early dry season months. So this is a trade-off we face. If we were to have requested these data to be acquired, we would have probably been charged $17 per square kilometer. And we all know that would be impossible. Okay, next slide. Now we got really concerned about things that hadn't happened. I got very concerned about the depths and also with the cloud coverage. So what we did is we used the bonus cloud cover and optical depth from the mode of that planet. And we had the same day, same area comparison between the digital load data in blue and the MIAC data in red. So the top figure, at least when we did this for, the digital globe accuracy was highly optimistic. Whereas with MIAC, we saw the filter decay. And then we looked at the aerosol optical depth. We thought we got worried, and so we got concerned about an aerosol optical depth of 0.6. Go to the next slide. So here we summarize the 0.9% of our empty data we did not process for some data weirdness problem. And we had aerosol optical depth greater than 0.6 or 3.7% or 4% of our study area. And visually determined cloud cover affected 5% of our study area. Nevertheless, in these areas, we mapped 700 million tree crowns. And these were mapped in the aerosol optical depths and cloud cover areas noted above the figure. We concluded that our aerosol and cloud effects on our data were lower down in 30 plus 20%. And for a while, we were very puzzled by this. But then we realized Martin Brandt has selected training data under high cirrus clouds, under high aerosol conditions. And those with that training data in conjunction with convolution enabled us to still map 700 million trees in this area. So this area actually comprised about 10% of our study area, because that also included 1% of our study area was disease and stop process. Next slide. Okay, let's go to the presentation screen. It'll be about 5 minutes. And so, what happened was we really surprised ourselves. We didn't realize how well we could do. We didn't realize, at least I didn't realize what the power of convolution was. But it's only as good as the training did. The first slide I showed, where we have a lot of Maxar data which we can use. And my thought is, it would be good to perhaps start as a foundational layer and map all the trees and bushes there. And if we have small footprint LiDAR or any other information we can use to go to carbon, we can do that. We can almost certainly do an earlier time period and a later time period. Now, this is an example of an aerosol optical depth of 1.0. On the right is here No, and the rest of our colleagues, Chris and Bill, from the allometry team. So these are some of the aerosol optical depths you have to worry about. And talk about dust storms. I wish I would have had a picture of what this dust storm bearing down on here and Patrice and Bill, because it's just like a very compelling dust storm image which Oct showed. Okay, next slide. We don't have our viewer. It can be found here at, it was written by two of our colleagues, Paul Morin and Shane Losper at the Polar Geospatial Center at the University of Minnesota. This enabled us to get out of this box we put ourselves in, that we had mapped 10 billion trees and converted them into carbon, but how the hell does anyone use them? So let's go to the next slide and see what that shows. Okay, this is just general guidance. Don't do this with Internet Explorer. Next slide. Okay, now this, I'll digress slightly. This is why if you use planet data, you're going to miss a lot of the smaller tree crowns. Planet data are on the order of between 3 and 4 meters spatial resolution. You can map a lot of trees, that's sure, but you're going to miss a lot of the smaller trees. So one of our trees, which we mapped and have seen before on the left-hand side with Maxar data, the big area is here, and you basically can't do too much for trees this size if you're using spatial resolution data of about the same dimension. Look at the next slide. Okay, so now this is looking at Sentinel-2, and Sentinel-2 is great. It's the best time series data at 10 meters. It's taken many of the things that were developed and proven to be extremely worth, great worth by the motive science team, and now they're moving down to do this at the 10-meter scale. They're great data for many things, but still they miss many of the small trees. Let's go to the next slide and see what that shows. Okay, this is just a few things. I don't think I go very far, but let's do it. This is using the viewer. We're going to fill in through that red box in nicer, which is where the Iara mountains are. Let's go in there. Okay, now you see we represent trees as areas. Let's zoom in further. You see this area is actually composed of 3 of our images. And in the viewer, the URL tells you what your zoom factor is and your longitude and latitude. And if you put that back in again, they'll go exactly to the same place. Next slide. Now we start to see pre-clouds. Now let's zoom in one more and then we'll stop. So now you see the individual pre-clouds. Let's go in one more just for the help. Okay, now we have 2 modes. One is the terrain mode and the other is the satellite mode. And the satellite mode, you can actually use the satellite map box background, which makes it very easy to understand the lay of the land and where you are. In the terrain mode, you only see the pre-clouds. Let's go to one more slide that's here. Okay, so now you can click on individual trees. See in the upper left-hand corner, the brighter green area. You can see the total carbon there, again, plus minus 20%. You can see the weight or the estimated fluid and weight carbon of that C3. You also see the location, and you also see the individuality of it and what the current area is or was. And then you have a link to the image which we use, and you can go to the Digital Globe website and you can actually look at that image. You may have to fiddle with it a little bit, but you have access to the raw data from their quick look images. So again, you see at the bottom, the URL associated with the viewer is very important for getting back where you need to be. And this concludes my presentation, but I hope to show that I think as we proceed with ARID, we have an excellent tool to use as a background to say we have now extensive and explicit data of pre-carbon over a 10 million square kilometer area. We can do something similar with modifications for the arid lands in the United States as a focus in the southwestern United States, New Mexico, Arizona, Utah, Nevada, parts of California. And then if we need to compare to other areas, we can do the same for Australia, for East Africa, or I can collect more data from elsewhere. Just depends on where there's interest and whatever could be useful to us to make the argument. We can do this not only in one location, we can do this in multiple places and then compare the results. Well, thanks for your attention, and thanks again to Steve Running for a great introduction. That saved me a lot of slides, and I really appreciate it, Steve. Woo!
Thank you so much, Jim. It sounds like maybe you have to go get a medical treatment right now. Are they coming for you?
Yes, I have to be infused for an hour with an antibiotic called vancomycin. So anytime you have a staph infection and it gets carried away, you worry about this going elsewhere in your body.
Yeah.
And the solution is to knock it down with intravenous antibiotics. So there are 2 that I'm taking, vancomycin is one, I forget the name of the other. I'm all hooked up and ready to go. You probably can't see, and I apologize for showing you. But, I think after 8 or 9 o'clock tomorrow, I can go home.
Awesome. Well, we're so grateful to you for spending your hospital time with us. We will make sure that any questions for you that came up in the chat make their way to you. The people who ask them will make sure you get responses to those questions. If anybody has other questions, feel free to put them in the chat or send them our way by email. Same for Steve Running. We went into past our time, and we want to recognize that people probably have to get somewhere, but this is the first of many discussions, and please don't hesitate to let us know. Also, the over 100 people who stayed on the call, if you shoot me an email, I'll bring you stickers and drink cozies to AGU or ship them to you. I'm so impressed by your perseverance and your general awesomeness. So thank you everyone so much for attending. We're really excited to have everybody as part of this team. Thank you. Thanks, Jim. I mean, we could have, it's been a long afternoon. We've held you here a long time. We could have discussion, or we could mosey to a place that has liquid refreshment and continue the conversation there. Does anyone have any burning thoughts or questions that they want to ask before we adjourn? You know how to get in touch with us. Please don't hesitate to do so. Look out. Like I said, we'll be at AGU, we'll have a town hall there. We'd love to see everyone there, get your ideas. And also, like we said, to show support for the project. There'll be program managers there watching. So, thank you all so much, and everyone online. Really appreciate you.
Yeah, for folks who are looking to continue conversation with drink, if we're gonna go to Gentle Ben, the drink and dinner, so well, yeah, folks will, we had a fairly small reservation, but there's plenty of room on the patio, so the more the merrier.
More the merrier. Please don't hesitate to come get your swag for you. But you're not seeing it yet. No, obviously, after you have that and you buy it. Talking about like